invited to give 35 years of my invention of state space averaging, but I really came to use this opportunity to announce some new technology that I'm developing, which promises to completely overhaul the way that switch mode power conversion is done by basically taking away the conventional square wave and all types of resonance switching, introducing new two switching methods which are called hybrid switching and storageless switching, which promise to completely revolutionize this field and change it into truly green technology, not in the 22nd century, but now. The future trend, which I didn't like, and that trend is going for the last 20 years. In 1988, I raised the actually doubt and question that the field is going in the wrong direction. They were actually, in order to reduce the size and weight because of pressure from consumers and so on, they went in the wrong way. They went to the very high, ultra high frequencies on megahertz. Now this trend continues to 3 and 5 megahertz. I think it's completely wrong because it's destroyed. The main objective is to make the high efficiency and small size. And they're not achieving that by going to high frequencies, because by the time they go there is too much loss and they have to put big heatsink, and then you're getting a point of diminishing returns. So the only correct way is to find proper new switching methods, find proper new technologies, converter topologies, and then do it at 50 to 150 kilohertz, which is really the operating range we should be working on. Thank you very much for this invitation and opportunity to share with you some of my recent work. I would like to start first by saying that Professor Dave Middlebrook was with us and at this conference a year ago. He is one of the founding fathers of the power electronics, not only in the United States, but worldwide. I had a great opportunity to learn from him over the years, from his teaching ability, from research skills, and just from respecting the man for who he is. So I'd like to ask the audience to please raise up and give a 1 minute respect for Professor Middlebrook. Thank you very much. Okay. State space averaging is at my talk. I was invited to talk about it like, let's see what happened past, but it turns out that just in recent time, I came up with some new switching methods, which I was quite pleased to see that my state space averaging, as I conceived it 35 years ago, works equally well for this new type of a converter topologies. And of course, today I can only give you a quick glimpse of it, but not a detail. And you will be able to chance to see me in exhibit booth 620 at Tesla Co. That I can answer many of your questions related to that. So this is 35 years anniversary. I did my PhD thesis in '76 and published a paper with Professor Middlebrook in 1976 at the PESC. However, this is also 35 years anniversary of my Cuk converter, coupled inductors, integrated magnetics, and duality in switching converters. And they are, in quite many ways, you'll see through my presentation, related to the state space averaging, and in fact helped its development. However, let's go back to the beginning. Professor Middlebrook started Power Electronics Group in 1970, and one of the first problems he tackled was how to model the converters. His first PhD student in this area, Gene Wester, tackled that problem in his thesis, and they published a paper in 1972 with deals with the circuit averaging. What is the circuit averaging is you develop the DC model of the switch and substitute in the circuit and come up with a steady state and AC properties dynamic model of the converter. However, there are certain limitations. This DC model requires that the switches are having a DC current, so you cannot implement it in an AC switch. For example, a simple forward converter, you couldn't implement it because there is AC switch there. There is here an example of a Tesla converter that this AC switch actually leads to the no DC bias magnetics. So it's very interesting, and yet it cannot be handled with the switch averaging method. Now let's go back to the past. When I had the state space averaging, when I conceived it, I wanted to be a general method such that you can not only model existing converters, but any future yet to be invented converters. And I succeeded that in that at that time, but it went even beyond my imagination, because my most recent work actually showed that it is equally applicable to some much more complex and more important converter topologies that we devised before. So it extends even to more now. So now, switch averaging actually is based on averaging a DC model of the switch. So it has to have complementary switches. So one limitation is it has to have always 2 switches, 4 switches, 6, etc. In other words, you cannot have 3 switches. State space averaging, on the other hand, is based on a fundamental principle that the steady state can be only established if you have a flux balance on inductances and volt-second balance and charge balance on capacitances. So therefore, criteria is shown on the state space averaging on the left. So here is example of a Cuk converter, 2 inductances, 2 flux balances, and charge balance on a capacitor. And you write this volt-second balance, and here is the balance equations for them. But now you can write them in a different way. Instead of writing them as a volt-second balance and charge balance, you can start with a circuit in the on position and write state space equation for that, or voltages for that equation on the left, and then write the equation for off time interval, and all you do is in the state space averaging multiply equations for on time with equation for off time, and here is your both DC and AC model. In the DC model, you just equate the DC quantities to 0, and you end up with the DC model, and then you perturb this steady state model, and you get your AC model. How do you get dynamic model? Well, here is the state space trajectories, and basically you are moving along this either on-time position circuit, linear circuit, or off-time. So you're moving in the is this working? I don't see the mouse working. Anyway, you are moving in both position, and the way to obtain the correct dynamic model is you have to take state space equation for on-time interval and state space equation for off-time interval, and with a weighting factor which is duty ratio on time of the switch. Of course, that results finally in a second state space equation, steady state, and dynamic model. And these equations here describe any DC model and AC model for all existing square wave switching converters, and all those existed at the time and those which were invented since that time. And that can be written in a single computer program to basically implement that. That was a first program we done at Caltech called SCAN, Switching Converter Analysis and Measurement Program. And basically, you had a very complex circuit. In this case, it was isolated couple inductor, isolated Cuk converter, which is 12th order system. And you draw it using menu-driven graphics on a PC. At that time, very first PC we implemented. And then the converter puts out all the poles and zeros, and you end up with the frequency response body plot. And I remember very well when I was making this demonstration, I would use a mouse and draw the circuit, and then here comes a frequency response. And one of the questions I got at one time was, can you do the opposite? Can you enter a frequency response and get the converter? Well, enter design, well, the answer is yes, we can. But in a different way, with a different program and different problem. We can solve the problem. Can you enter desired DC voltage gain and draw all converters which belongs to that DC voltage gain, not only those which are known, but also have a computer come up and with different converter topologies. Actually, I posed that problem to my research group at Caltech at the time, and I said, look, if you have this solution for steady state, which is there, all we can do is look at the topology of interconnection, which will be basically shown as just some ones and zeros in these matrices and minus ones to describe interconnection, use a steady state criteria for state space averaging, and if these linear equations have a unique solution, that converter exists. If it doesn't, then that converter doesn't exist. Well, it turned out that if you have just 2 inductors and 1 capacitor and put them in all possibilities, I think you might be surprised that there is over 1 million possibilities. Of course, how come so many people in this field only come up with a few converters once in a while, okay? Because at that time, computer program established there are only about 30 working DC to DC converters. Well, I was glad to see that Cuk converter was one of them too. And this problem was actually solved by I call him a 5-star PhD student, Dr. Maksimovic, and he came up with a very, brilliant enumeration process, how to enumerate all these different possibilities. And here is his incidence matrices, which were basis for it. And as you see in matrices, there are ones, minus 1, and zeros entries. And he came up with an ingenious method how to insert the switches, and in fact, all the way down to implement it in switches, down to transistor and 3 diodes in this D-square converter. So this was a new converter named 243,146-.2, okay? So now, with this, I was sitting back in one of these conferences where we usually gather some of my former PhD students who were already professors at other schools and current PhD students, and we are sitting around a table, and I think one of my students, Kai No, said, okay, now with the Dr. Maksimovic solving that, that spells out the death to the converter topologies. I apologize to Dr. Maksimovic. This is my best rendering of him that I could do on a computer. But where there is a birth, there is a death, there is always a birth. And here I introduce you to the birth of a lot of converter topologies which are popping out of this crib, which I call a hybrid switching method. And again, I emphasize the topologies are consequence, and the key is a new hybrid switching method. Well, what is this hybrid switching method able to do? Let me give you just a couple of examples. I think you're all familiar that if you want to make an isolated boost converter, about the only way you can do it at the present time is using the full bridge type boost converter, which has 4 active switches on a primary and 4 diodes on a secondary. Well, it has 1 inductor and 1 transformer. Here I give you another alternative. Here is another isolated boost converter with the same gain function, 1 over 1 minus d, same transformer. Actually, transformer is even better, but we don't have time to go into it. And only 3 switches. So I gather, well, it's better having 3 switches than 8 switches. And the only price you pay is there is little inductor in a series with a diode named CR1, which is called LR. That resonant inductor is about 40 times smaller than a regular PWM inductor. I'll get into it in a minute. Well, now we showed we can reduce the number of switches and have an identical configuration with identical properties, operated by duty ratio, constant switching frequency, and so on. Can we do now the opposite? If you go from 2 switches, like your regular common synchronous buck that everybody uses, can we put 3 switches, add extra switch in it, and make it more efficient, smaller size, and at the same time less costly? And my answer is yes, we can. How? Well, you can see here a configuration which essentially, in addition to the regular tapped inductor buck with the 2 switches, I just add 1 transistor, 1 extra switch, and 1 capacitor, and extra switches in series with the resonant inductor, and obtain a converter which essentially has the main diode rectifier switch or synchronous rectifier, which sees 4 times smaller voltage than you would see in a synchronous buck, which translates into 16 times lower silicon area needed. So you have much less silicon area needed, and you have a higher efficiency and still small size. How? Because this transformer is not acting as a double duty. It's not only, I call it a hybrid transformer. As a transformer for inductive energy transfer, it is essentially operating and stepping down the voltage from input and stepping the inductive current. But this, during off-time period, this capacitor discharges through resonant inductor in a load through the primary winding, and transformer acts as a current multiplier. So then you have a 2 times or 3 times higher current on a secondary. So therefore, you get much higher step down. So here is example at a 50% duty ratio, you have a 5-to-1 step down with just a 1-to-1 turns ratio one turns and one turns on a auto transformer or this hybrid transformer. If you have 2 to 1, then you have a gain function that from 12 volts you get immediately 1.7 volts at 50% duty ratio, and at the same time much lower stresses on a main high power switch on the output. So this is just one example. There are many more and we don't have a time to go through all of them. But let's see now how does the state space averaging applies to that. Well, first present we have, well, you'll also see that the picture at the top looks like pretty much familiar to you. If you short the diode CR1, which is shown in the red, that basically is a Cuk converter, isolated, non-isolated polarity inverting. Now just put a diode in a series with it, you lose the step-down function, and it just operates as a 1/1 minus D boost converter. And you can see here the first boost stage is really like a boost, and the second, at the bottom, you have this translation stage. So the boost voltage is translated through these resonance circuits to the output. And that's how you essentially have here equivalent circuit model that the boost stage is reduced to simple resonance circuit. And the key point is that this resonance circuit is now driven with the AC ripple on that capacitor, not the DC voltage differences, but AC ripple, because DC voltage differences is 0. Because the ripple is 10% of the DC, and you have also factor of 4 reduction, you have about 40 times smaller flux on that resonant inductor than on a main PWM inductor. So here is in a nutshell what is the hybrid switching. Well, during on-time interval you have a resonant inductor present, but a resonant capacitor is actually has a dual role. During the on-time interval, it operates with this resonant inductor in a resonant mode, but in an off-time interval, it operates with the PWM inductor in a regular linear mode, and it's connecting the two things together because voltage on capacitor has to be continuous. So this capacitor is switching back and forth from resonant mode to linear mode each cycle, and each one is limited to its own interval. Single stage bridgeless PFC converter with isolation. It's well, now you can use the same converter, but relocate a resonant inductor in the center, and you can just put isolation. You can put AC source on the input with no bridge. Why? Because you can see here, positive input voltage polarity is essentially operating the diode in such a way that positive polarity operates the CR2 diode during off-time interval, and then when input voltage polarity changes, it actually redirects which diode has to conduct for which interval. So automatically, without diode bridge, you have actually bridge action. So can be, here flux balance, now state space averaging, how it is applied? Well, we just apply flux balance for a PWM inductor at the top and a flux balance for a resonant inductor at the bottom. But that one's limited only during the on-time interval, and that leads to the fact that voltage on that resonant capacitor must be 0, DC voltage, which you plug back in the equation and you get the regular equation of the boost converter. Now for the negative interval, the opposite happens. For the negative interval now, there is a DC bias on this resonant capacitor, but when you plug that into the flux balance equation for inductor, you get the same voltage gain. So that's a proof that converter works in a boost mode in both ways. How to implement it? Well, you implement this switch as a first and third corner switch with the 2 MOSFETs. Well, that's another big important feature. How do you put isolation? Each time you put isolation, you lose a lot because you have to now increase the stresses and voltage of the switches, flux is big and so on. Here, this comes with basically no penalty. It operates the same as a non-isolated version. In fact, you will recognize that this transformer is the same as a Cuk-type transformer, is an original Cuk converter. It's essentially single-ended transformer with a full flux balance. As it is shown here in blue, it has both flux directions, no gap, and all advantages of the single-sided transformer. What's the applications? Well, now you can use the transformer to scale it up and down. You can scale it to 48 volt for telecom applications. You can scale it to 12 volts for data centers, or 200 volt for say hybrid vehicle, lithium-ion battery chargers or so. Well, interesting feature is this is really not one converter of the boost type. You get 2 converters in one, because from a 0 duty ratio up to this resonant duty ratio called DR, converter operates like a step-up, step-down converter. So you can start it from zero duty ratio in a soft start mode and then eventually change over to step up function. Single stage three-phase rectifier. Well, I'm glad that I was able to, as a tribute to my idol Nikola Tesla, to make some contribution in a three-phase to DC conversion. Up to now, we were doing the three-phase, and of course three-phase that Nikola Tesla invented and all the AC system is really how the whole system in the world is now utilizing electricity, and he electrified the world with his three-phase system and AC motors. However, we are still not doing justice to his three-phase system when we are converting into 2 DC, because we are using three-phase and first convert it into intermediate DC voltage, and then we use isolated DC to DC converter which has to store a DC energy, which is really not taking full advantage of his AC system. Well, what would be the better way of doing it? How about using these 3 isolated converters, each one in each phase of the converter, each one having, for example, 98% efficiency, and then putting them in, operating in parallel. Therefore, power is processed in parallel, but notice all the currents are 3-phase currents which are now added on the output. So in fact, the output capacitance can be essentially practically eliminated. There is no storage needed on the output because each phase is providing the right current at the right time. And each phase converter is shown with a simple 3-switch converter, and isolation is done at a high frequency. So you do direct AC to DC conversion, and of course, if your DC is a DC transmission line and AC is AC transmission line, you have a perfect converter which can connect AC to DC both ways bidirectionally in a high efficiency, low cost, small size system. State space averaging future. Okay. Well, there is a burst of a storage-less switching method in this crib, and there is a bunch of the baby converters coming out of it which are implementing this storage-less switching method. What is a storage-less switching method? Remember the previous view graph I showed that basically now this resonant capacitor is actually not changing the role. It is always resonating, except he's now, during on-time interval, resonating with one resonant inductor, LR1, and during the off-time interval, he's resonating with the other resonant inductor. What is the big advantage of that? Well, remember previous PWM inductor was rather big. Now this PWM inductor is eliminated and converted now into 40 times smaller resonant inductor. So now we get a magic. We can make a very, very small converter with a high efficiency and small size and low cost. How does the state space averaging apply to it? Well, simple extension. You apply the flux balance on the first resonant inductor for on-time interval and flux balance for a second resonant inductor during off-time interval. While the resonant capacitor resonating during both periods, you have to apply a charge balance for resonant capacitor during both intervals for a whole cycle. So that's the only difference. And now we go to modern power supplies needed for computer servers. We can use, for example, this bridgeless PFC in front that I just introduced, but then you can use isolated storage-less converter. Now, this is the first converter which, for the first time, we are doing something which should have been always done in a DC to DC. DC to DC conversion shouldn't store any energy. Yet all the present DC to DC converters store the energy either in the output of DC inductor or input inductor which carries the DC. This converter has only one magnetic piece, and this is an example of about 500 watt converter operating close to 98% efficiency, 97.8, which essentially has only one magnetic piece which never saturates. You can put any current through it, and it is operated not as a resonant converter, although it looks like and smells like resonant converter, but it's operated at a constant switching frequency and variable duty ratio. So you can regulate it and put any current through it without saturating the transformer. You see the characteristic of the efficiency over a wide range is basically staying at the same efficiency. Why? Because all switching losses, all kinds of switching losses are eliminated. All what's left in a converter is conduction losses of the switches and conduction losses of the wires or magnetics. These are losses at 300 watt or so. We have 8 watt loss and so on. Then we have, now what is the magic? What is the magic with all of this? Well, the magic is that we forgot when I introduced the Cuk converter in, that was 1976 or so, that was the first converter in addition to CPIC at the time, which was introduced at the same time, which had a capacitive energy transfer. And all converters, isolated and isolated up to now, were based on just inductive energy transfer and the switches and no capacitance at all. Now here's a comparison what you can do. If make a buck converter at 750 watt at 50 kilohertz, you'll have this inductance on the left-hand side. But to get the same power, 50 volts and 15 amps, on the output, you use a 6 little capacitance. Each one is carrying a 3 amp RMS ripple current for a total of 18 amps. And you use a much smaller, 40 times smaller inductor. Which one is easier? This capacitor is really costing you a few cents compared to the big inductor. And the big point is that the efficiency of that whole system is over 99%. We're talking about 750 watt with about 8 watt loss at the full power. So no heat sink needed and much smaller. And the big thing, this is operating at 66 kilohertz, okay? This is another goal I set out in '88. I said I'll go from 500 kilohertz down to 50 or 60 kilohertz, and true to the fact, I did that. Now, I think I have 40 seconds for my concluding remarks. I would like to invite all the forward-looking companies, as well as I would say, people who are engineers who want to accept the challenge to join me to convert and make a power electronics green dream technology and do it now and not wait for another century. And you can, in the final comments, this will be posted on the internet, so we don't need to read it, but here is what Professor Middlebrook had to say, made remarks on a switch averaging method in our 3-volume book on a forward, and this is what he remarked on a state space averaging. And finally, my concluding remark is, I know there will be a lot of questions. That's why I decided to come to this conference and specifically have exhibit booth at Tesla Co. for booth number 620, where I can answer many of your questions. I have also projector, so I can entertain any and explain you how these new methods work. So I'm looking forward to see you there, and I will be there this evening as well as tomorrow and Wednesday. Thank you very much for your patience. You have been a great audience. Thank you.